Welcome back, and as alluded to at the end of the last video, we do have another rule called the constant multiple rule, which just means that if we have a number that's a constant in front of a function, right, the constant can be pulled out and then we differentiate the function as normal. That's what we saw previously, right? The 3, for instance, just stayed there and ended up being multiplied by the 5, okay? Big deal. And then the other thing, sum and difference rules, as you might expect, if we have a sum or difference of functions, right, you can differentiate each function. And why is that? Well, it's actually based in the limit. And so this is actually a nice opportunity for us to do a proof that you could actually do on your homework or on a test. So if we wanted to prove this, right, we have to start with the left-hand side and work to the right-hand side. So I would do ddx of f of x plus or minus g of x, right? And so then now in order to do this, we have to remember the definition of the derivative. That is that we have the limit as h approaches 0. And then the numerator would be f of x plus h, right? But our f of x would be f of x plus h plus or minus g of x plus h, okay? Because we have, that's our function. And then we would subtract f of x, right? But f of x is f of x plus or minus g of x, okay? And then all over h. Okay, so now what I'm going to do is I'm just going to play with this a little bit. So I'm going to say distribute the minus and to f of x and g of x and rearrange. So if I rearrange this, so let's see, limit h approaches 0, I'd have f of x plus h, and then I could move that f of x next to there. Okay, so move that f of x over, and then that would be kind of one piece, and then there is a plus minus in front of the g of x, which I could factor out, and then I'd have, you know, g of x plus h. You can probably see where this is going, minus the g of x all over h, okay? And now what I'm going to do, I'm going to say, this next step, I'm going to say because f and g are differentiable, so I'm using my hypotheses, right, for differentiable functions. So I know the derivatives exist. So because these are differentiable, I can say this is the limit as h approaches 0 of f of x plus h minus f of x. So I know these limits exist, so I can use the limit laws and break them up. Limit as h approaches 0 of g of x plus h minus g of x all over h. And lo and behold, if we write this out, this is f prime of x plus or minus g of x, okay? Or g prime, rather. Okay, and we're done. Okay, that's the end of the proof. Okay, so again, not anything terribly difficult, but you just need to kind of work through, start with the left side, prove the right side, and then make sure to use your hypotheses. Okay, so there we go. Let's look at a couple examples and then we'll wrap this video up. So equation, find the equation, the normal line of the parabola below that is parallel. Oh, okay. So first of all, what's this normal thing mean? This you might have to look up, but again, normal, the definition of normal is that it's perpendicular to the tangent line. Okay, so, okay, don't know about that yet, but, and then here's the parabola. Find the equation of the normal line to the parabola below that's parallel. Okay, hang on. So this parallel, right? Okay, so I need to rearrange this just so I can see this as a line, right? I know it is a line because it's a, both exponents have exponent 1, or both variables rather have exponent 1. So let's see, that'd be x minus 5 is equal to 3y. So then that's the same as saying 1/3 x minus 5/3 is equal to y. Okay, so then this is my slope, right? So that means the slope is 1/3, which means what? The tangent slope, okay? Okay, so just to be clear, the line that we're working with should have a slope of 1/3, okay? But then the normal line is perpendicular to the tangent line, so the tangent slope, if we need that, is -3, okay? Okay, but now I need a line, right? So a line needs a slope and a point. I have a slope, I don't have a point. What do? Well, I haven't used this yet, okay? And actually, if I look at y prime, the derivative, as we saw before, that's the slope of the tangent line at any given point of the function, right? So this is the slope of tangent line, okay? And if I do y prime here via the power rule and sum of difference properties, right? I can say this is 2x, right? Bring the 2 down, subtract 1 from the exponent, and then -5, okay? Oh, and that should actually be equal to -3, right? Because of the tangent slope that I have over here. So then let's say I get 2x is equal to 2, x is equal to 1. And then if I put that 1 in, let's see, if I put in 1, I get 1, -5 is -4, and then 0. Okay, so I get the point 1 comma 0. Okay, so then therefore, my line using point slope form is going to be y minus 0 is equal to 1/3 x minus 1, and I could certainly distribute if I want to, but this would be the equation of my normal line. Wasn't that fun? So just keep in mind that the line that we're working with, if it is parallel to this, right, that gave us our slope of 1/3, which then if that is our normal line, that should be perpendicular to the tangent line, right? So that means the slopes must be negative reciprocals of one another. And that allowed us to go on. And once we found the derivative and set the derivative equal to our tangent slope of -3. All right, next couple exercises. So find the points on the curve where the tangent line is horizontal. And it would help if I had a function. It looks like it disappeared. Here is the function that we're supposed to work with. F of x is equal to 2x to the third plus 3x squared minus 12x plus 1. Don't know why that disappeared, but it's there now. Okay, so then where the tangent line, okay, so tangent line, I have to look at the derivative. And so let's see. The derivative would be 6x squared plus 6x minus 12. And the derivative is the slope of the tangent line. If I want that slope to be horizontal, right, that means that this must be equal to 0. Divide everything by 6. X squared plus x minus 2 equal to 0. Factor x plus 2, x minus 1 is equal to 0. So then I get x is equal to -2 and x is equal to 1. And so then I just have to go through and find, when x is -2, what do I get for the y value? It ends up being 21. And when I put in 1 for x, I get out a -6. Okay, so those are the 2 points where the tangent line is horizontal. Again, slope of the tangent line is given by the derivative. And then if we want the tangent line to be horizontal, just set it equal to 0. Next one, intervals of concavity are determined by this second derivative, right? Bendiness has to do with the second derivative, so I have to do the first derivative. Okay, first derivative gives me, what, 3x, 3x squared minus 8x and then plus 5. Second derivative, which is what I really want, 6x minus 8. Okay. And so then if I, set this equal to 0, x is equal to 4/3, that is a possible point of inflection, okay? Again, where the second derivative is equal to 0 is a potential point of inflection. So what do I need to do? I need to check it. So I do my little chart, okay? And on that chart, I'm going to put 4/3, right? And I'm going to say, let's do some test points. I'm going to do f double prime of 0 and then f double prime of 2. If I put in 0, I get something that's negative, less than 0. So then that means this is concave down, and then it's partially answering my question. And then if I put in 2, I get something that's greater than 0, so that's concave up. So all I'm going to say is that it's from here, it's concave up on the interval 4/3, comma 0, or comma infinity. Now I did it this way. You could have just found the second derivative, set it greater than 0, and solve. That's fine. I like analyzing it just in case I happen to need to know if 4/3 was a point of inflection as well. Okay, but so punchline being, you could do this work in less time. Okay, so that's you see exponential functions are coming up, but that's going to be in the next video. So for now, just remember we have these two rules, the constant multiple rule and sum of difference rule, and we saw some examples of them.